In this video, we are going to look at 10 complete worked hypothesis test examples. We can sort them in a couple of different ways. We can sort them by parameter. We have 4 tests about the mean or average of a population, 3 tests about the proportion, which is synonymous with the probability or percentage of a population falling into a certain category. And we have 3 tests about the variance and standard deviation. And remember, a test for either of those is by definition a test for the other one. If you want to know if sigma is bigger than 10, you're testing to see if sigma squared is bigger than 100, and vice versa. Okay, we could also sort these by distribution. We have 3 tests that are t-tests based on the student's t-distribution, 4 z-tests based on standard normal distribution, and we have 3 chi-squared tests. Finally, we could sort them by tails. We have 3 examples of left-tailed tests, 3 examples of right-tailed tests, and 4 examples of two-tailed tests. So our 10 problems are going to be divided up into 4 different scenarios, and we'll do a few hypothesis tests for various scenarios. So our first scenario is ocean life. We have some information being given to us about data collected about the length of great white sharks around the Farallon Islands and the length of whale sharks in general. Okay, so this sample data is going to be reused a couple times, and we will bring it back as we need it for each problem. Okay, so I'll give you a second to read through here. We are going to do 3 hypothesis tests in scenario 1. Okay, we are going to use a 0.01 significance level to conduct these hypothesis tests. So we're going to be a little extra conservative about our decision making when it comes to rejecting the null hypothesis here. So the first one we want to know, or the first thing we're going to try and test, is we want to know if we can conclude that the average length of mature female great white sharks at the Farallon Islands is more than 14 feet. The second theory, or we can look at it as testing a theory or trying to answer a question about the population, right? There's a sign at the Monterey Bay Aquarium, and it reads the standard deviation of the lengths of mature female great white sharks at the Farallon Islands is 2.5 feet. We want to know if that's a true statement. So again, evaluating the truth of the statement is evaluating the truth of a theory, a hypothesis. And finally, the third question we're going to investigate here is, are less than 50% of all whale sharks shorter than 25 feet long? So our first example. In this first example, we want to decide if we can conclude that the average length of mature female great white sharks at the Farallon Islands is in fact more than 14 feet. Okay, so first step in any hypothesis test is to figure out the hypothesis you want to test. And as long as that's something that can potentially be proven, okay, then we will use that as our alternative hypothesis, because the alternative hypothesis is what we're going to attempt to prove. In this case, we want to know if the average, the mean, mu, okay, so the average of all the female great whites around the island, is more than 14 feet. Okay, so we want to write this statistically. Our alternative hypothesis is going to be that mu, the mean, is greater than 14 feet. So the average length is more than 14 feet. That's what we're going to set out to attempt to prove. The null hypothesis is going to be our starting assumed to be true theory. We are going to assume that the mean is equal to 14 feet and no longer until we see some proof. So the null hypothesis always comes for free from the alternative hypothesis. Okay, so let's go look back at the data we had earlier when the scenario was presented. Okay, so what do we know about the length of female great white sharks around these islands? Well, we have a sample of 94 sharks that had an average length of 14.7 feet and a standard deviation of 3.1 feet. Again, because this information is about the 94 sharks, they are a sample. They're not all the sharks that live near the island or frequent the island. So This average is a sample mean, okay, and the standard deviation is the sample standard deviation. So statistically, we're going to write these as n, my sample size is 94, my sample mean x bar is 14.7, and the sample standard deviation is 3.1 feet. Okay, so this is the information we have to test our theory. The average in our sample was 14.7 feet. That's longer than 14 feet. So from the sharks we've seen, we have some evidence that makes us believe that the average overall for the entire population might in fact be greater than 14 feet. Okay, now we've already chosen alpha. Alpha is 0.01. Okay, so the next thing we need to do, okay, is choose our test statistic, the equation we're going to use. And in that process, it's important that we note here, we're told to assume that the lengths are normally distributed. And so when we go to determine which equation, we're going to take a look at our formula sheet. When we're using our formula sheet to decide what formula is the appropriate one to use in a situation, we always start from left to right. So first thing, what are we interested in? In this problem, it's the mean. Okay, so now we have a couple of options depending on what else we know. Okay, so we know the standard deviation of the sample of great whites, not all great whites. So sigma is unknown to us. So we're going to follow this path on the formula sheet. Okay, so first thing we have to see when our required conditions are looked at, first option, X is normal. So are the lengths of the sharks in our population normally distributed? And we were told to assume that's true. Okay, so now, one thing to note real quick here is we don't really need that assumption normality for this particular problem, because even if our population that we're sampling from, if the lengths of all sharks, great white sharks, are not normally distributed, our sample size of 94 is still way bigger than 30, so we would be able to proceed using the same techniques. Okay, so our sample mean x bar is approximately normal, but because we don't know sigma, we know S. When we try and standardize the sample mean, we end up with a t-score. Okay, so this last formula, x bar minus mu divided by S over the square root of n, that is our test statistic formula. The resulting test statistic is a t-score from the student's t-distribution. And so we're going to plug in our numbers. Okay, so let's remind us what we know. We know n, x bar, and S, so those are going to get plugged in. And then notice finally, again, when we are executing the hypothesis test, we are always assuming the null hypothesis is true until proven otherwise. So our null hypothesis says assume mu equals 14. So when we calculate our test statistic, we assume mu equals 14. So now that we have our test statistic calculated, it's time to determine the p-value. Okay? But to do that, we have to know if it's a left, right, or two-tailed test. Otherwise, we don't know what part of the graph represents the p-value. So in determining if your hypothesis test is a left, right, or two-tailed test, we have two things to consider. First, what are we trying to be convinced of? Because remember, the definition of the p-value is the probability of getting our data, so the n, x bar, and S we have, or more convincing data, assuming the null is true, so assuming mu is 14. So the part of that definition that hasn't been satisfied, and the part that determines a left, right, or two-tailed, is the or more convincing data part. So I'm trying to be convinced that the average mu of all the sharks is greater than 14 feet. When I look at my sample, the single largest factor is going to be the sample mean, the average of the sample. Okay. So here my sample mean is bigger than 14 feet. So for the sharks I've seen, yes, the average was 14, but samples are random. So we have to decide if this 14.7 foot long average for our sample of 94 sharks is enough to convince us. Now, what would be more convincing than the average 14.7 we have is a bigger value for x bar. If our average was 15 feet, if the average of the sample was 17 feet, right? If our average was 91 feet, that would be more convincing than 14.7 feet. So the bigger X bar is, the more convinced I am that the mean of the entire population is big. Okay? If you want to be convinced something is true population-wide, the more you see that trait in the sample, the more you start to believe it's not random chance that's causing you to see that trait. Okay? So, more convincing data, again, MCD for short, is a big X bar. Now, that is only half of the process of determining if this is a left, right, or two-tailed test. So, now that we know more convincing data would be a big X bar, remember we converted our X bar to a t-score, so we have to see what would happen. So, a big X bar would translate into a big t-score. So if we replace that 14.7 with 18, we would end up with a number bigger than the 2.189 and change that we have there. So big X bars are represented by big t-scores. When we go to graph our t-distribution, the big t-scores are to the right towards positive infinity. So first I had to decide what more convincing data was, and then I looked at the test statistics and said, if I got the more convincing data, how would that be reflected in my t-score? So now that we know the p-value is the area to the right of our test statistic, that's what we mean by right-tailed test. It means the p-value is the area to the right of your test statistic. Okay. We need to find the area to the right of, and again, I put 2.9 on here. That's rounded for the graph and for the graph only. Okay. We don't want to use that rounded number in our calculation. And again, our formula said that the t-distribution was going to have n minus 1 degrees of freedom. So 93 degrees of freedom because n, my sample size, was 94 sharks. So my p-value, okay, because it's based on a t-distribution, I need to find the probability that is shaded on that t-graph using the TCDF. Okay, and you notice here, I want everything to the right of my test statistic, so I'm going to start with my test statistic, and I'm not rounding it in the TCDF. I'm using the full 2.189274774 all the way up to infinity with 93 degrees of freedom. When you do that, you're going to get a value that's approximately 0.0155 for your p-value. Okay, now, the p-value itself, that's kind of like the final numerical calculation. Generally, we're going to round that to 4 decimal places. Keep in mind, what are we doing with the p-value? We are always comparing it to alpha. Alpha is typically going to be 0.01 or 0.05, so 2 decimal places. So as long as we don't round our p-value down to 2 decimal places and create a tie that didn't really exist, as long as we have 3 or more, so I had to go 4 just to be careful, just in case. So rounding that p-value to 4 decimal places is always going to give us enough accuracy to compare to alpha. Okay. Now, more decimal places are actually always better. Once I have my p-value, we're almost finished with the hypothesis test. We're ready to draw our conclusion. Again, so this is my p-value, the probability of getting a sample of 94 great whites with an average of 14.7 or longer, okay, assuming the average of all the sharks is 14 feet. So the probability of seeing the sample data we saw or longer sharks randomly, if the true overall average was 14 feet, is 0.0155. So that's about a 1.5% chance of seeing this randomly if the actual mean was 14. So the probability of our sample mean being this big or bigger if the average was 14 is extremely low. Okay, but it's not lower than alpha. We said alpha at the beginning of 0.01 for this particular problem. So even though the random chance of this happening is very low, it's still not so low that I'm convinced that it's not random chance. No. So our p-value is not less than alpha, barely. So I failed to reject the null hypothesis. I came close to rejecting the null hypothesis, but This is like being almost convinced, but I'm just not quite ready to say, okay, I believe it for sure. It's settled. Right? So once you know what you can or cannot say about the null hypothesis, in this specific case, we are rejecting the null hypothesis. That tells you what you can or cannot say about the alternative. Again, the alternative is the alternative to the null hypothesis. So because we failed to reject the null hypothesis, then the null hypothesis HO might be true. We tried to rule HO out and we failed. Okay? Because the null hypothesis could possibly be true, then I am not comfortable declaring the alternative H1 to be true. That's where we get this idea. Okay? So let's go back to the original problem, because a conclusion that is reject or fail to reject the null, or I can or cannot support the alternative, doesn't answer the actual question. The question that was posed to us to start with was, can you conclude that the average length of mature female great white sharks at the Farallon Islands is more than 14 feet? So let's look at what we decided. Okay? We failed to reject HO, so we failed to reject the theory that the average is exactly 14 feet. Okay? So the average could be 14 feet. Okay? And because of that, we cannot support the alternative. Okay? So we haven't proven that the average is more than 14 feet, because 14 might be the right number. Probably not, because our p-value was very close to being less than alpha. So I'm almost ready to reject the null hypothesis, but I still have a little hesitation. Okay, now let's look at this in English. Again, the alternative hypothesis, the average length is more than 14 feet. That's what we wanted to know if it was true or not. So we want to phrase our final conclusion in that manner. So again, there's not enough evidence to conclude that the average length of mature female great white sharks at the Farallon Islands is more than 14 feet. Notice how complete this statement is. It doesn't just say, we can't say the average is more than 14 feet, okay? Or we can't prove mu is greater than 14. We want to be very specific. We started with a, fairly simple, straightforward question about the length of female great whites at the Farallon Islands, and we want to answer it there. We don't want to get all statisticky in our final conclusion. Now, again, how did I come to this particular sentence? And again, the English language is fantastic. There's probably 100 different ways you could write a sentence that has the same meaning. Okay, so I want to acknowledge that up front. Okay, the key really is about the meaning. So again, let's go back. We cannot support. Okay, why can we not support something? Because we don't have enough evidence. So there's where my beginning here comes in. I'm going to say there's not enough evidence to include, again, because I didn't have enough evidence to support. Okay, now what can I not support? That's H1. H1 was that mu is greater than 14. Okay, but in words, that is the average length of the mature female great white sharks at the Farallon Islands is more than 14 feet. So we came close, but we did not prove beyond a reasonable doubt, so to speak, that's what alpha is, that the average of these sharks is more than 14 feet. Now, if I was forced to bet money, I would bet the average is more than 14 feet. Okay? But if I had to bet $1 billion on it, I would hesitate, because again, we weren't completely convinced based on our sample. Okay, so now let's look at the next example. Example 2. So there's a sign at the aquarium. It says the standard deviation of the lengths of mature female great white sharks is 2.5 feet. We want to decide if that's a true statement or not. So that's a theory, an idea that we have to test the validity of. Okay, so again, alternative hypothesis is always the first step. So we were asked about the standard deviation of all the female great whites at the island. So we were asked about the standard deviation of the population. Right? And we want to know if that is 2.5 feet. Okay, so now here's where we have to be careful in creating our alternative hypothesis. So the alternative hypothesis here is going to be that sigma, the standard deviation of the population, does not equal 2.5 feet. And we have to do this because it is impossible to prove equality. Okay, so there is no sample that would prove to me beyond a reasonable doubt that the standard deviation of all the sharks is 2.5 feet. Okay, so this is the only time we have to take what we're asked and change it to fit the tools we have. Okay, so if I'm going to set out to attempt to prove that the standard deviation does not equal 2.5, the assumption would be that the standard deviation is 2.5 feet. Okay, so my starting hypothesis is we'll assume this is true, and then we're going to set out to try and prove it wrong. It's the best we can do. And statistically, it is impossible to prove equality. You can never prove mu or p or sigma or any other parameter is equal to a specific number. Okay, so get back to the same information we had for the previous problem. So we have a sample of 94 that had an average length of 14.7 feet and a standard deviation of 3.1. So we still have n, x bar, and s the same as they were in example 1. Okay. So we've developed our hypotheses. We know alpha. Next thing we got to do is pick our equation, which again, the assumption of normality is important here. We have to keep this in mind. So to determine the equation, we go back to our formula sheet one more time. So as we look at our formula sheet one more time, again, we work from left to right. We are interested in answering a question about the population standard deviation based on the sample standard deviation S. So it's the behavior of S that we need to understand. So when we look at our required conditions, the only condition that's required is that the population we're sampling from is normal, right? We were told to assume this in our problem. Now, understand, this is a critical assumption. If this turns out not to be true, then nothing we do in the rest of this problem would make any sense or be valid in any way. And here, there is no sample size option. So unlike when we tested the mean in example 1, even if we didn't assume that the lengths of the great whites were normally distributed, our sample size would have been big enough to make up for that lack of normality. Okay, that's fine when we're testing the mean, not for testing the standard deviation or variance. Okay, so we don't know exactly how S squared is going to behave. That's going to depend on some features, but we do know that because the population we're sampling from is normal, S squared can be and must be converted or transformed into a chi-squared score using this equation. Again, check out the formula. The degrees of freedom on the chi-squared is the subscript n minus 1. So sample size minus 1 will be my degrees of freedom. So let's go back and calculate our test statistic. We've chosen our equation. Again, we need n, s, and sigma, or s squared and sigma squared. Either way, if you know s, you know s squared, and if you know sigma, you know sigma squared. Okay, so n is 94, s is 3.1. Okay, so that's where I get my numerator from. Again, as with every single hypothesis test, we are always assuming that the null hypothesis is true. So we're assuming that sigma equals 2.5. So I'm going to plug 2.5 in for sigma. I get a chi-squared score just under 143. Now, that's the exact value. I didn't round that. It just came out to be 4 decimal places. Okay. So we have picked our equation, plugged in our numbers, got our chi-squared score, our test statistic. So now, in order to find the p-value, we have to decide if it's right, left, or two-tailed. Okay, so the p-value is probably getting our data or more convincing data, assuming the null is true. Okay, so our data and assuming the null is true, those two were used when we calculated the 142.9968. The whole key to left, right, and two-tail starts with more convincing data. What are we trying to be convinced of? We're trying to be convinced or trying to prove that the standard deviation sigma is not 2.5. So I'm going to look at the sample standard deviation. Currently, that's 3.1. Okay, so my sample standard deviation is a little bigger than 2.5. So I have some evidence that 2.5 is the wrong number for the overall standard deviation. Now, the farther away from 2.5 S gets, now that could be lower than 2.5 or higher than 2.5, either direction, right? The farther away from 2.5 feet my standard deviation is in the sample, the more convinced I am that the standard deviation of the population, sigma, is not 2.5 feet. Okay, so more convincing data in this case could be represented by a very small value of S, something way less than 2.5, or a very big value of S, something bigger than 2.5. Okay, like 3.9 would be bigger than the 3.1 we have now. So again, only half of the job of determining right, left, two-tailed is determining what more convincing data is. Then we have to look at the equation. So looking at our equation, right, S is right here. The smaller S is, you place 3.1 with the smaller number, we get small chi-squared scores. You place 3.1 S with a big number, like 10, you get a giant chi-squared score that would be way bigger than the 142.9968. So we have two things that could do the convincing for us. We have a small value of S, which would transform itself into a small chi-squared score. On the chi-squared graph, the small scores are on the left tail, close to 0. And we could also be convinced that sigma does not equal 2.5 if our sample standard deviation S was really big. Really big chi-squared scores are the result of big values of S. And so we could also be convinced if our chi-squared score was on the far right, towards infinity on our chi-squared graph. So because our test statistic could be either really small or really big, we have what's called a two-tailed test. Okay? I could be convinced if my chi-squared score was farther away from the center of the chi-squared graph than we currently are. So again, degrees of freedom is n minus 1. Our sample size was 94, so we have 93 degrees of freedom. Very critical thing to point out here, right? I have a chi-squared graph with 93 degrees of freedom, so the mean of this graph, not to be confused with the mean or average length of the sharks, has nothing to do with that. We've left the sharks behind and turned everything into chi-squared scores. But on a chi-squared graph, your mean is equal to your degrees of freedom. So I know that the mean, which is roughly in the center of my graph, is going to be 93, which tells me that 142.9968 is over to the right of that mean. And again, so our test statistic is representing our data is too big side of the argument. Okay, so that is going to be half of my p-value. Okay, but I had to know that the mean was 93 to know that the 142.9968 was on the right and not on the left side of the graph. Right, your test statistic could be representing either end of the graph. On a two-tailed test, you have to know which tail it's representing. Okay? So we would be equally convinced if we had a small chi-squared score, something like maybe 65, I don't know. We don't even care what the exact equivalent of being too low would be to 142.9968 being too high. All we care about is that if we were on the left side of the graph, we would be equally convinced at some point. And so we're going to look at how convincing is our data on the high side, and say equivalent data on the low side would be just as convincing. So the area we see is only half of our evidence. So to calculate our p-value, we need to take the area we have in the right tail, the shaded region in blue, and double it. So I'm going to do 2 times my chi-squared CDF, again chi-squared CDF because our test statistic, the equation resulted in a chi-squared score. I'm going to go for my test statistic 142.9968 to the right, so up to infinity, with 93 degrees of freedom. Okay, now you can actually put the 2 times in with the chi-squared CDF and have it do the calculator do the calculation all at once. But I did want to point out here, if you did the chi-squared CDF by itself, the output would say 6.7 and a bunch of other numbers, but finally at the end, e to the minus 4. It's very critical that you see that e to the negative 4 over there. That's scientific notation, which means you have to move your decimal place 4 to the left. So instead of being 6.7, it's actually 0.000, then 6704151215. Okay, I have to move the decimal place 4 to the left. The first move to the left puts it in front of the 6. And then I got 3 more moves to the left, which will give me 3 zeros to start the number off. Of course, that has to be multiplied by 2. So ultimately, I end up with 0.0013. Now, that's my p-value. That's the probability of my sample standard deviation being this far away from 2.5 or farther away from 2.5, assuming the population standard deviation really is 2.5. And so it's about a 1 in 1,000 chance that we randomly see a sample standard deviation this far away from 2.5 if the real standard deviation was 2.5. So we have very convincing data. Specifically, again, from the beginning, we don't just say, hey, I think the p-value is low enough, I'm good to go. We have set our limit of 0.01 for alpha. Our p-value is less than that, so we are going to reject the null hypothesis. Okay. So we're saying the null hypothesis was false, and because we have ruled the null hypothesis out, we have eliminated the null hypothesis from possibly being true. That means we're going to support the alternative hypothesis. Again, it's the only alternative we have to the null hypothesis, which we just rejected. So going back to write our final conclusion, again, the alternative hypothesis was that the standard deviation is not 2.5 feet. We have supported that. So we're just going to make a declarative statement saying that the standard deviation of the lengths, again, being complete, the lengths of mature female great white sharks at the Farallon Islands is not 2.5 feet. We have been convinced beyond a reasonable doubt, okay, that the standard deviation of these sharks is not 2.5 feet. Is there a chance we're wrong? Yes, it's about 0.0013. Okay, about a 1 in 1,000 chance that we would be wrong if we make this decision based on what we've seen. So, again, looking at what we've decided, we decided we're going to support H1, so we're going to declare H1 to be true. So I just need to start off by declaring the what? That's where H1 comes in. The standard deviation, specifically of the lengths of the mature female great white sharks at the Farallon Islands, is not 2.5 feet. I'm making a statement, declaring it to be true, period, end story. So now we're going to look at our last ocean life example. Okay. Early on, we asked, are less than 50% of all whale sharks shorter than 25 feet long? So in determining alternative hypothesis, we want to know if less than 50%, so this is a question about the percentage of the population, or synonymously the proportion of the population that do something. Okay, so this is a question about P, the population proportion. Anytime we're talking about the proportion of items that do something, they have to fall into some category, or the percentage of values is the percent that fall into some category. The category here happens to be that they are shorter than 25 feet long. Okay, so alternative hypothesis is what we're going to set out to prove. We're going to attempt to prove what we're asked to attempt to prove if it's something that we can legally potentially prove. And we can prove more or less or not equal to. We just can't prove equality. So my alternative hypothesis is exactly what I was asked. Okay, only, again, we're asked if less than 50%, And to do the math correctly, we have to change that percent, 50%, into a proportion, 0.5. Otherwise, our numbers will be off by a factor of 100. So we want to know if the proportion of sharks that are shorter than 25 feet, again, whale sharks, is less than 0.5. Okay? We will assume that the proportion is 0.5, that 50% are shorter than 25 feet long, that the percentage is no lower than 50% until we see the proof. Okay? Again, we're assuming that the alpha is 0.01. So what do we know about whale sharks? Okay? So we were given a sample of 83 values, okay? 83 measured sharks, and 35 of them were found to be shorter than 25 feet long. So this is our sample data. So again, we had 83, that's my sample size, 35 of them being the 83 whale sharks in the sample. So 35 out of 83 met the condition of being shorter than 25 feet long. So I have my sample size N is 83, and my sample proportion is 35 out of 83. So the ratio of how many are shorter than 25 compared to the denominator, how many we checked, 83, is 35 out of 83, or 35 83rds is the proportion of whale sharks in our sample that were less than or shorter than 25 feet long. Now, symbols are critical. Notice here we have P, we have P hat, and in a minute we're going to get to P value, which is not the same as the value of P. Okay, so we have our hypothesis, we have our sample data sorted out. Again, it's time to determine our equation. One more time back to the formula sheet. When I go to the formula sheet, again, this time we're testing the proportion, okay, or percentage. Again, proportion less than 0.5 means a percentage less than 50%, which also means that the probability that a random whale shark is shorter than 25 feet would be less than 0.5. Those are all different ways of saying the same thing. So we're interested in the proportion P, using the sample proportion P hat to test the value of P. So when we look at our required conditions, since the sample has been taken, this first condition is the only thing we have to worry about. F, the frequency, has to be bigger than 5. So we have to have at least 5 whale sharks that were shorter than 25 feet. Okay, so that's our frequency that are in the category. N minus F is the frequency that would not be, right? That's the leftover sharks. So with our case, right, we had 35 sharks that were shorter than 25 feet. So the remaining sharks, the 83 minus those 35, those are the leftover that are not less than 25 feet, would be the N minus F. So we have 35 and then 48 that are not less than 25 feet. So we have more than 5 that do and do not fall into our category. So we're good to go there. So because we have enough representation of being in and out of our category, P hat is approximately normal, okay, which means we can transform P hat into a z-score, which we are going to do in our hypothesis testing. We always convert to the ZT or chi-squared score or any other distribution in other problems beyond Math 115. So I'm going to use the formula P hat minus P. We're going to compare our sample proportion to the assumed proportion P, see how far off that is, and compare that to the standard deviation of P hat. Okay, so we're going to standardize P hat basically, turn it into a z-score, because we know how to find probabilities. All right, now that we have our equation, we're going to plug in our values. Again, N is 83, P hat is 35 over 83. We're going to plug those in for P hat and N. Now, I want you to notice in the numerator, we have to have those parentheses around the P hat minus P so that that subtraction happens before the division. So we're going to plug in, again, the 35 over 83 for P hat. Notice I didn't round that. Any rounding of P hat could cause us trouble. Again, that's going to make our z-score off, which will make our p-value off, which means our final conclusion could be completely wrong. So critical, when p hat is a fraction that does not simplify down to a unrounded decimal, leave it as a fraction. Leave those parentheses on top. And again, last time I want to remind you, we are always assuming the null hypothesis is true, so we're assuming that p is equal to 0.5. That's from HO. So we plug that in everywhere we see a p. And we get this negative 1.42693538, which is perfectly fine because that's a z-score. And remember, z-scores go from negative infinity to positive infinity. And so once we've figured out our z-score, we have to decide if it's a left, right, or two-tailed test so we can find our p-value. So again, what am I trying to be convinced of? That p, the population proportion, is small, less than 0.5. So we look at the sample proportion. The smaller that sample proportion is, like 34 out of 83, 25 out of 83, 1 out of 83, those would be more convincing that p is small than the current p hat of 35/83. So the smaller p hat is, the more convinced I am that the actual population proportion is small. So in your sample, the smaller the proportion that fall into the category that you see, the more convinced you are that the population proportion of being in that category is also small. Okay. So you can simplify this down. More convincing data in this scenario is a small p hat. We're not done. All right, so to finish off deciding if it's a right, left, or two-tailed test, we have to see what would happen if we did in fact get a smaller p hat. So small p hat is the 35/83, that's the p hat we have. If we replace that with something smaller, like 20/83, that would result in a smaller z-score, a bigger negative number, but remember, bigger negative numbers are actually smaller numbers overall. So a small p hat means a small z-score. When you go to our graph of a z distribution, the small z-scores are towards negative infinity on the left side of the graph, which is why this is a left-tailed test. So our p-value is the area to the left of negative 1.42693538 on the z-graph. So again, on my graph, I rounded the z-score to save space. Okay? But when I go to use my normal CDF, I'm not going to use that rounded 1.43. So we want the area to the left of our test statistic. So our lower limit would be negative infinity. Okay? And our upper limit would be our actual test statistic. And remember, z has a mean of 0 and a standard deviation of 1, so I have to enter those as my last two parameters inside the normal CDF. And we get a p-value a little bigger than 0.07. Okay, so when I compare that to alpha, my p-value is not less than alpha. Remember, that's our test. Is the p-value less than alpha? Yes or no? In this case, no. 0.0768 is not less than 0.01. Because my p-value failed to be lower than alpha, I failed to reject the null hypothesis. Okay, so because the null hypothesis is still a possibility, I cannot endorse or support the alternative. So we've decided in terms of rejecting or failing to reject the null and failing to or can or cannot support the alternative. We decided what we can do there, but we need to answer the question that was originally posed to us. So we were asked, are less than 50% of all whale sharks shorter than 25 feet long? So we determined that because we failed to reject the null hypothesis, we are unable to support the alternative. So that's what we're going to say. We are unable to support the alternative. So there's not enough evidence to conclude that less than 50% of all whale sharks are shorter than 25 feet long. Again, how do I get to this conclusion? Well, I cannot support. I lacked evidence to support. So that's where the there is not enough evidence to conclude comes from. What did I lack the evidence to support? H1, and H1 was that P was less than 0.5, okay, which means the percentage was less than 50%. Okay, so that's where I get the less than 50% of all whale sharks are shorter than 25 feet long. So now we're going to move on to our second scenario, company salaries. So we have a company that has 3,589 employees. Every one of them is paid a monthly salary. So they don't get paid by the hour. They each get a fixed amount each month. Okay. We're told that the company-wide average, right, per month is $6,340 with a standard deviation of $1,964. So one month the company decides to give each employee an equal lump sum bonus. So everybody's going to get the exact same amount added to their check. Okay. So the only thing we know is that we've been told that in the month that the bonuses were distributed, 325 random employees, so that's a sample of the 3,589 total employees. So for that sample, they were paid an average of $8,171 each. Okay, so this is what we know. We're going to use a 0.01 significance level one more time. And we're only going to do one hypothesis test here. We're going to test to see if we can say that the bonus amount was $2,000 per employee. Now, keep in mind, every employee was paid the same bonus, which means originally the monthly average was $6,340. If everybody got a $2,000 bonus, then the average would go up $2,000, right? You remember our transformations from earlier in the semester. So what we really want to know is the average in the bonus month for all 3,589 employees, right? That's our population, $8,340. If that's true, then the bonus amount was in fact $2,000 per employee. Okay, so this is the fourth example we're going to look at. So in order to try and determine if the bonus was $2,000, we have to determine if the average is 8,340 or not. Okay, so this is about the average, mu, and we want to know if the average is in fact 8,340. Okay, remember, can't prove equality. So when it comes to alternative hypothesis, what we're going to set out to prove is we're going to set out to prove that the mean, the average salary for the bonus month is not $8,340. Because if the average is not $8,340, then the bonus is not $2,000. And it's the bonus we really want to know about. Okay, the average is a means to an end. Okay, as I said a minute ago, right, it's impossible to prove equality. There's no sample that would make us be convinced beyond a reasonable doubt mu equals exactly 8,340. So that's why we're going to attempt to prove that the mean is not $8,340. This is the only time what we're asked to prove is not what we actually attempt to prove. Otherwise, whatever we're asked is usually going to be your alternative hypothesis. So let's go back and look at what information we had about the company salaries. Okay, so we have a average and standard deviation of the company in a normal month. Okay? And then we have a sample of 325 employees. So we have a sample of 325 employees in the bonus month, and their average, so their X bar, was $8,171. Okay? The standard deviation, we don't know what it is for the sample of 325, but we know before the bonuses, the standard deviation was $1,964. So I have a sample size of 325, a sample mean of $8,171, and a population standard deviation of $1,964. How do I know that's sigma? So we have to go back to something we talked about previously, right? So we know in a typical month, the standard deviation for the whole company is $1,964, and we have added an equal amount to everybody's salary. So remember, that's going to change the mean by however much was added to the individual salaries. The mean salary will go up by that much, but the standard deviation after the bonuses will be the same as it was before the bonuses. So we know in the bonus month, the standard deviation is still going to be $1,964 because that was what the standard deviation sigma was before we added the bonus money in. And adding the bonus money is changing the average, but not the standard deviation. Okay, so understand, this really is a rare situation. We know sigma. Sigma by definition is the average distance from mu, the population mean. We don't know the value of the population mean because we don't know what the bonus was. So this is a scenario where we're saying we know the average distance between the individual paychecks and the unknown average paycheck. Okay? So this is why it's a rare situation when you're testing the mean or average that you actually know sigma. 999 times out of 1,000, if you're going to test a theory about the average or mean of a population, you're going to be doing the t-test based on the fact that you know S and not sigma. Okay, but here we do know sigma. So again, once we know what we're testing and what information we have to do the test, we have to determine which equation to use. We go back to our formula sheet. We're testing a theory about the mean. This time sigma is known, so we're going to go to the top line of our formula sheet. Okay. So we don't know that the population is normal. In fact, the individual salaries of the roughly 3,600 or so employees are almost guaranteed not to be normally distributed, much more likely to be skewed right. Think of the chi-square graph, because what's going to happen? The bulk of your employees are going to make, right, around the same amount of money, give or take a little bit. Their managers will make more than they do. But then there's the vice presidents, right? The assistants to the vice presidents, the presidents of the company, the CEO of the company, right? With that many employees, there's going to be an upper echelon who make way more, right? $200,000, $300,000, $700,000 a year, maybe even millions a year, okay? As opposed to the 30, 40, 70, maybe 100,000 that most of the employees are making. So we don't have a good reason to believe that the population we're sampling from, the salaries are normally distributed, but we do have a sample of 325. So even though, right, I firmly believe that the population is probably not normally distributed, the individual salaries, I do have a sample size that is big enough, more than 30, 325. So X bar will be approximately normal, which means we can convert it to a z-score since we do know sigma. Okay, so here's the formula we're going to use to execute this hypothesis test. So X bar, N, and sigma are all known to us. We'll plug those in. Remember, we are assuming that mu is true, so I'll plug in 8,340 for the mean. We get our z-score coming out here again, unrounded. Parentheses on top are critical, right? Without those, you're going to divide the 8,340 by that denominator and then subtract that result, which you don't want to do. So again, you also need the parentheses on the bottom because you don't want to take the top, divide it by 1964, get an answer, then divide that by the square root of 325. So it is critical that you have all the parentheses here. We got to determine if it's right, left, two-tailed test. So what are we trying to be convinced of? That mu does not equal 8,340. So we look at the sample mean. That is our key witness, our main impact on what we believe might be the truth about the population mean mu. So to convince me mu does not equal 8,340, X bar needs to be far away from 8,340. And the farther away from 8,340 X bar is, the more convinced I am that mu does not equal 8,340. So, bottom line, more convincing data in this scenario is either a very small X bar, so something much less than 8340, or a very big X bar, something much bigger than 8340. So we have two options that we need to track down. X bar could be really small or really big. Again, we have to look at the equation you're using. So X bar directly impacts the value of the z-score. The smaller X bar is, the smaller that z-score is. The bigger X bar gets, the bigger the z-score gets. So two options: small X bar, which means small z-scores. Okay, small z-scores are in the left tail of the z-graph. We'd also be convinced if X bar was too big, which means that we'd have big z-scores, so our z-score could be in the far right tail. Combine those two possibilities together, and that means we have a two-tailed test. We would be convinced that the alternative hypothesis is true if our z-score went too far in either of the tails of the z-graph. So I draw my z-graph. Again, the mean of a standard normal distribution is 0. My test statistic, rounded for the graph only, is negative 1.55. That's to the left of 0. That's representing the X bar is too small. So that's half of our evidence. That's half of our p-value, right? We could be on the far right of this graph and be just as equally convinced as we are right now. So I have to take that area and double it. So 2 times my normal CDF. Because my test statistic is in the left tail and it is a two-tailed test, we find that area in the left tail and double it. So once we get our p-value, approximately 0.1208, I compare that to alpha. That is very much not less than 0.01, so I failed to reject the null hypothesis. And as always, when you fail to reject the null hypothesis, that means you cannot support the alternative. You have two options. If you cannot rule one out, you cannot say for certain the other one is true. That's what's going on here. So we set out to determine if the bonus amount was in fact $2,000 per employee. So what can we say about that? Well, formally, we tested the average, okay? And we came up with that we could not support the alternative hypothesis because we failed to reject the null hypothesis. So there's not enough evidence to conclude that the average salary for the month where the bonuses were given is not $8,340. Okay, so again, how do I get that conclusion? Okay, break down the phraseology here. I cannot support. Why can I not support something? Because there was not enough evidence to support it or to conclude that it's true. Now, what is it I cannot support? I cannot support the theory or the statement that the average salary in this month is not $8,340. So, now, again, I'm not done because they didn't ask me about the average salary this month. They asked me about the bonus, right? So, okay, but if I'm unable to say that the average is not $8,340, that means I'm also unable to say, because I don't have enough evidence, that the bonus amount was not $2,000 per employee. So, again, once I determined what I could or could not say about the average, that told me what I could or could not say about the bonus. Okay, we know what it was before the bonus month. Okay, so it is possible that the bonus amount was $2,000 per employee. Right? So assuming that the bonus was $2,000 per employee, it was reasonable to see the evidence we saw in a sample of 325 people by random chance. Now, notice I am not concluding that the bonus was in fact $2,000, just that it could be, it might be. Okay? It's possible that the bonus was $2,000, making the average $8,340 this month. So let's move on to a new scenario. The Big Bang Theory. Okay, so for those of you who are fans of the show, you know that Sheldon and Leonard have a game. Okay? Rock, paper, scissors, lizard, Spock. So bigger than the standard rock, paper, scissors game. Okay? And they often use this to decide who gets to make a decision when they don't agree. Okay, so we have data here about what Sheldon has chosen in a sample of 100 games, and we're going to use that evidence to try and predict what Sheldon might do in a game in the future. So also have some information here about the Nielsen ratings. Okay, so we're going to answer some questions about Sheldon's strategy and the Nielsen ratings. Now, important on the ratings here that you notice the units, right? The average we're given of 16.5 million viewers, that is in millions. So 16.5 would represent 16.5 million. Okay, and that's going to come in really important when we go to do the math. So for these problems, we're going to use an alpha of 0.05. So we're going to be a little less conservative, right? So on those first four problems, we had to be convinced very significantly, less than a 1% chance that we'd be wrong if we rejected the null hypothesis. Now we're going to allow ourselves a 5% chance, which is actually the most common. Okay, so for this scenario, we're going to do 3 hypothesis tests. So examples 5, 6, and 7 overall. So if I challenge Sheldon to a game, is it safe for me to assume that the probability he's going to choose Spock is going to be 0.28? Okay, so we're going to test the probability that Sheldon chooses Spock in a random game. Okay. We want to know if we can conclude that the average number of viewers for all episodes, right? So that's all 14 seasons. We want to know if that average is less than 17 million viewers per episode. And then we're going to make a decision about the standard deviation in the number of viewers for all 14 seasons. Okay, so we're going to use this information to test these 3 theories. Let's dig into example number 4. All right, so for our first hypothesis test in this scenario, example number 5 overall, right, I've challenged Sheldon to a game of rock, paper, scissors, lizard, Spock, and I want to know if I can assume that the probability he chooses Spock in a random game is 0.28. So in developing my alternative hypothesis, we want the probability. Probability is always probability that something specific happens. So in this case, the probability he chooses Spock. And I want to know if that probability is 0.28. So the probability he chooses Spock is 0.28 if the proportion of times he chooses Spock is 0.28. So this is a proportion question. Now remember, it is impossible to prove equality. So no sample data would make me believe that 0.28 is the perfect probability. So I have to attempt to prove that the probability is not 0.28. So we have some sample data. We have Sheldon's choices in 100 different games. Okay, so based on what we've seen of his behavior, we're going to use this to predict his innate strategy choices. So we have a sample of 100 games, and he chose Spock 36 times. So in our sample size is 100 games. The proportion of the sample, p hat, that Sheldon chose Spock is going to be 36 out of 100. Now here, 36 100ths is exactly 0.36, so there's no rounding of p hat. So it's all right for me to use the decimal version here. It's not going to create rounding error. Now, in a previous proportion example and future ones, we left the fraction alone because we did not want to round. Again, here I'm not rounding, so we're okay. So now that we know what we're trying to prove and the evidence we have to attempt to prove it with, as always, we go pick our equation, we hit our formula chart, we're after probability or proportion, we have to check, do we have at least 5 sample values that are in our category? So in our sample of 100, did we have at least 5 times where Sheldon chose Spock and 5 where he did not? Yes, we cleared those easily. All right, so p hat is approximately normal, and we can standardize p hat to a z-score, which is what we're going to do. So we're going to do a z-test. So we're going to plug in 0.36 for p hat. Remember, we're assuming the null is true, so all those p's become 0.8 from the null hypothesis. We need the parentheses on top. All right, need to make sure we're taking the square root of everything on the bottom. So you want to verify that you get 1.718411613. Notice there, I'm not rounding that. That's everything I had on my calculator display. Okay, that's as unrounded as I can keep it. So we have to know if it's a right, left, or two-tailed test. So what are we trying to be convinced of? That the probability does not equal 0.28. We look at the sample. The sample proportion is going to try and convince me about what the real proportion or probability might be. And the farther away from 0.28 that the sample proportion is, the more convinced I am that the real probability or proportion is not 0.28. So bottom line here, the more convincing data in this scenario is either p hat being much less than 0.28, very small p hat, or p hat being much bigger than 0.28. So looking at our equation, right, p hat directly influences the value of the z-score. Small p hat means a small z-score. Big p hat means a big z-score. Okay? And the small z-scores are on the left tail towards negative infinity on the z-graph. Big z-scores are in the right tail towards positive infinity. So this is a two-tailed test. Right? Our z-score could be very small or really big. So the farther the z-score gets away from the mean of 0, the more convinced we are that the real probability of him choosing Spock is not 0.28. So my test statistic happens to be positive z-score representing a big p hat, because remember, Sheldon's p hat was more than 0.28. And so it came out as a positive z-score, the high side of our two options, but that's only one of the two options. That's why that shaded area is half of my p-value. We need to find that area and double it. So I'm going to take 2 times the result of the normal CDF. And I've said this before, I'll keep saying it 1,000 times. It's okay to put 1.78 rounded on the graph, but inside the normal CDF, I don't want to use that rounded number. I want to use the best number I can for as long as possible. Ultimately, I get this p-value 0.0779, which is not less than my alpha of 0.05. Get your p-value compared to alpha every single time. So we failed to reject the null because the p-value was not small enough. Because we failed to reject the null, we cannot support the alternative. Okay, so time to write the conclusion here. So we failed to reject the null, we cannot support the alternative, meaning there's not enough evidence to conclude that the probability he chooses Spock in a random game is not 0.28. Important to notice here, the not applies to the 0.28. Okay? We're not saying that the probability he does not choose Spock is 0.28. We're not negating the Spock choice, but rather the probability of making the Spock choice. And again, the reason I'm making this conclusion, again, I lacked evidence. Okay, that's why I could not support something, and the something I could not support was H1. So I didn't have enough evidence to prove that the probability he chooses Spock in a random game is not 0.28. Now I want to be clear, this feels like a double negative. It feels like we haven't proven anything, which is officially true. We haven't proven anything. But let's think of this from a practical standpoint. We tried to prove the probability he chooses Spock is not 0.28 and we failed, which means most likely the probability is close to 0.28, not too far off. So if I go into my match with Sheldon and I assume the probability he chooses Spock is approximately 0.28 or close to that neighborhood, that gives me pretty good insight as to what I should or should not choose myself if I'm going to try and defeat him. So when your goal originally is to set out to prove equality, you usually have a reason for believing in that number. So when you fail to prove that number wrong, right, it's often okay to use that number moving forward, knowing you never proved it to be true, but it's probably in that same neighborhood. That is if you fail to reject the null hypothesis. Now, had we rejected the null hypothesis, I would know the probability is not 0.28, and assuming 0.28 would be a really bad idea. Okay, so let's look at a few more examples. So now we're going to investigate the Nielsen ratings for the show. So we have a sample, and we want to know if the average number of viewers for all the episodes, for the entire run of the entire series, is less than 17.1 million. So again, this is what I want to decide. This will determine my alternative hypothesis. So I'm interested in the average, and I want to know if the average is less than 17.1 million. So remember, my units are in millions, so I'm going to just use 17.1 to represent 17.1 million. Okay. So I'm going to attempt to prove that the mean is less than 17.1. Remember, we can possibly, potentially prove more, less, or not equal to. So since that's what we're asked, that is our alternative hypothesis. We only have to turn things upside down when we're asked about equality. Okay, so we will assume that the average was 17.1 until proven otherwise. Now, what do we know? We have information about the ratings for 28 episodes. So that's a sample of the 14 seasons, right? So we have a sample of 28 episodes. That sample had an average, an X bar of 16.5 million and a standard deviation of 1.2 million. So the data we have is N equals 28, sample of 28 episodes. The sample mean is 16.5. Remember, the units are in millions. And the standard deviation is 1.2 rather, excuse me. Again, those units are millions. Now, could we put the full number in? 17.1 million, we could write that as 17,100,000. We just have to make sure 16.5 million was written as 16,500,000 and S was written as 1,200,000. As long as you put all the zeros in for everybody, then they'd eventually cancel out and we'd be okay. So, once again, as it was true in a few of the other examples, so we've checked the data and it appears that the viewers were normally distributed. Okay, so we're going to go ahead and make that assumption in determining which equation to use. Once again, to determine which equation to use to perform our hypothesis test, we go back to our formula sheet. We have a theory about the mean or average number of viewers. Okay. We don't know the standard deviation for all of the episodes. We only know for 28 episodes. Okay, so we're under the sigma it's unknown option. Okay. We were told to assume the number of viewers is normally distributed. Now, as a quick side note, here this assumption is very important because our sample size is only 28. So remember, when we had a sample size of 325 for the average salary a little while ago, we didn't need to know that the population we were sampling from was normally distributed because the sample size made up for that lack of normality. Here, our sample size is close to being big enough to make up for the lack of normality, but not quite big enough for the limit we set. So, because we're assuming the population we're sampling from is normal, X bar is going to be approximately normal. When we standardize X bar, since we don't know sigma, we have to estimate that with S. We're standardizing to a t-score, not a z-score. Okay, so we look at our equation, plug in all of our values. Again, parentheses on top and bottom, don't lose those. We're assuming the null is true. That's why 17.1 goes in for mu. And everything else came from the sample. Okay, we have to decide if this is a right, left, or two-tailed test. We're trying to be convinced that the mean average rating is less than 17.1 million. We look at the sample ratings we have. We have some evidence that the average might be less than 17.1. We have to decide if that's convincing enough or not. That's why we have to do the full formal hypothesis test. Now, the smaller that sample mean is, right, the more convinced I am that the mean mu is small. So 16.5 is smaller than 17.1. I have some evidence that the population mean might be less than 17.1, right? A smaller sample mean, like 14 million in our sample, would be more convincing than the 16.5 we currently have. So more convincing data in this scenario is a small x bar. Looking at our equation, small x bar leads to a small t-score. Small t-scores are in the left end or left tail of the t-graph towards negative infinity. We draw our graph. T-distribution graph, symmetric, mean of 0, looks a lot like z. Again, 27 degrees of freedom because our sample size was 28. The formula sheet tells us n-1 degrees of freedom when we use this formula. This is a left-tailed test, is what we determined a minute ago, which means the p-value is the area to the left of our test statistic. So I'm going to use my TCDF because I have a t-score. The area to the left of, and again, inside the TCDF, I'm using the full negative 2.645751311. Don't shortchange or round that. Okay, 27 degrees of freedom. We get the p-value 0.0067. Okay, that is definitely less than alpha of 0.05. Because that's less than alpha, I am going to reject the null hypothesis. Remember, alpha is your limit. If you cross that line, you're comfortable rejecting the null hypothesis, and we cross the line. We dip below 0.05 for our significance level comparison. So because we reject the null, and again, when I say reject the null, I mean we're saying the null is false. We're convinced beyond a reasonable doubt, not 100% because we haven't seen the entire population, but based on what we've seen in the sample, we are convinced beyond a reasonable doubt, alpha is my reasonable doubt, that the null hypothesis is false. And because of that, I'm equally convinced that the alternative to the null must be true. So let's put this into language of our problem. We are supporting the alternative hypothesis, so we're going to declare the alternative to be true. So we're just going to make a statement. Now, I could preface this if I wanted to with there is enough evidence, okay, to say that the average number of viewers for all episodes of the Big Bang Theory is less than 17.1 million viewers. 100% perfectly reasonable. For me personally, I find that to be a little redundant, right? If it's sunny outside, I don't go around saying there's enough evidence to say it's sunny outside. I just say it's sunny outside. Okay. When you make declarative statements, you usually just make the statement. You don't say, I have enough evidence to say this is true. Again, just a matter of taste on my part. So, again, we're supporting, so we're saying something is true. That's where the beginning of this comes in. And then what are we saying? What are we declaring? We're declaring that the average number of viewers for all episodes of the Big Bang Theory is less than 17.1 million viewers per episode. Again, averages are always per whatever. So in this case, per episode. Okay. Moving on to our last Big Bang Theory example, we're going to test the standard deviation. And so we were asked to see if the standard deviation for all 14 seasons, so that's for the population, okay, is greater than 0.85 million. So I want to know if sigma, the standard deviation of the population, is greater than or more than 0.85 million. Again, units are in millions, so 0.85 is enough here. We're going to use the same data we tested the mean with in example 6. Okay, so we have a sample of 28 episodes. We know X bar is 16.5 and S is 1.2. I know those are X bar and S and not mu and sigma because they are for the sample of 28 episodes, not for the entirety of all the episodes of all 14 seasons. Again, we're assuming that the number of viewers are normally distributed. Once we have our hypotheses figured out, we know how convinced we need to be, alpha set, we know the information we have to do the test, we pick the equation. Back to our formula sheet, we've been down this route a couple times before already in this video. So we're after the standard deviation, the population must be normal. We were told to assume the number of viewers are approximately normally distributed. So distribution of S is a little funky, but it is directly related to a chi-square distribution. And our degrees of freedom will be our sample size minus 1. So plugging in all of our numbers, assuming the null is true, we get a chi-squared score of 53.8 and change as displayed on the screen. Now, is 53 a big chi-squared score? Sometimes yes, sometimes no. It all depends on how many degrees of freedom we have. That's why we have to do everything formally. Can't just look at the numbers and go, oh, that's big. Okay, so we have to figure out if it's left, right, or two-tailed test. Alternative hypothesis is what I'm trying to be convinced of. So you want to convince me sigma is bigger than 0.85. S needs to be big. The sample has to have a high standard deviation for me to believe the population has a high standard deviation. And the bigger S is, the more convinced I will be that sigma is big. All right? The higher the sample standard deviation, the more convinced I get the population also has a high standard deviation. So big values of S are what we would consider in this scenario more convincing data. Looking at our equation, right? We want big values of S. Big values of S make for big chi-squared scores. Again, because that S is in the numerator, the bigger S is, the bigger the final outcome is. Means these are always right-tailed tests. And when I say these, I just mean the fact that we want big chi-squared scores. So the fact that I want a big chi-squared score makes this a right-tailed test. I draw my chi-squared graph. 27 degrees of freedom because my sample size was 28. So n 28 minus 1 is 27. A minute ago, I asked if 53.8 was a big chi-squared score. Turns out in this case it is, because the average chi-squared score when you have 27 degrees of freedom is 27. So my test statistic, 53.8, is over there to the right of 27. This is a right-tailed test, meaning wherever my chi-squared score was, the area to the right is the p-value. So we use our chi-squared CDF from our test statistic, and again, unrounded test statistic, 53.8131487.9, less rounding here, less rounding in the end. We get that tiny p-value, 0.0016, very much less than our alpha 0.05. So I am rejecting the null because my p-value is low enough that I'm comfortable rejecting the null. Because I'm comfortable rejecting the null, I'm comfortable supporting its alternative. Again, that's why we call it the alternative. It's the alternative to the assumed null. So the question we were asked was if we could say the standard deviation in the number of viewers for all 14 seasons of the show is greater than 0.85. Again, we're supporting that alternative hypothesis. So we're declaring something to be true, so we're just going to make a statement. Okay, so we're supporting, and that's why I'm just saying here it is, here's the truth. And what am I saying is true? What am I declaring true? That the standard deviation sigma is greater than 0.85. So, and again, I don't just say sigma is greater than 0.85. We put this in full context. The standard deviation in the number of viewers for all 14 seasons of the show, The Big Bang Theory, is greater than 0.85 million viewers per episode. Our fourth and final scenario is going to be about the Iditarod dog sled race. The Iditarod takes place each year from Anchorage to Nome, Alaska. There are two courses that alternate each year, a north and a south course. Each one are approximately 1,000 miles long. They adjust the course each year for safety concerns to make sure it's a safe course. And we have some information here about finishers of the race and how many calories the dogs consume in a day. So we're going to do 3 hypothesis tests about the Iditarod. For these tests, we're going to use a 0.05 significance level. So the first thing we want to try and decide the truth about is whether or not we can conclude that more than 15% of all Iditarod finishers are female. Okay. So can we conclude that the variance in the number of calories consumed per day by the dogs that are competing in the Iditarod is less than 1 million calories squared? Remember, Variance is in squared units, so that's where the calories squared comes in, and why the variance number there is so high, because it's a number that's already been squared. And then finally, we want to know if we can determine that the average number of calories consumed per day by the dogs is 10,000 calories. So for the 8th example, so for this problem, we are to determine if we can say that more than 15% of all Iditarod finishers are female. First, we have to come up with our hypotheses. So what are we trying to decide the truth about? We're trying to decide if something is more than 15%. Okay, so the percentage is what's in question. Percentages are directly related to proportions. Percentage and proportions are always the percentage or proportion that fall into some category. Here, the category is finishers that are female. And so when I write my alternative hypothesis, we're going to try and prove that more than 15% of all Iditarod finishers are female. So we write this in terms of proportion P, because our formulas are in terms of P. So we want to prove that P is greater than 0.15. Let's take a look at what we were given about the finishers. We were told that 57 of the 295 were female. So we have a sample size of 295, a sample proportion of 57 out of 295. Next, we're going to find the equation. So we got to go back to our formula sheet. So looking at the formula sheet where it's in proportion, we have to have our frequency. So in this case, the number of females, which is 57, definitely bigger than 5. With 295 total finishers that we have data about, we have way more than 5 that are not female. So P hat is approximately normal. And our formula is going to be our z-score formula that we've used a few times before already in this video. Our sample proportion is 57 out of 295. So we're going to plug that in. We're going to plug in 0.15 for P because, as always, we are assuming the null hypothesis is true. And so now we have to determine if this is left, right, or two-tailed. More convincing data. What are we trying to be convinced of? That P is greater than 0.15, that the percentage of female finishers is higher than 15%. So when we look at our sample, P hat needs to be more than 0.15. And the bigger P hat is, the more convinced I am that P is big. So the higher the proportion of finishers that I see are female in the sample, the more convinced I am that there's a higher percentage of female finishers in the population of all finishers. So one more time, ultimately, more convincing data in this particular situation is a big value for P hat. Looking at the formula we're using, right, big values of P hat are going to directly lead to big values of z-scores. And the big z-scores are to the right, and towards positive infinity on our z-graph. So this is a right-tailed test, meaning our p-value is the area to the right of our test statistic. So to calculate that area, we're going to use our normal CDF because we have a standard normal distribution. Again, not using the rounded version 2.08 for the z-score that I used on the graph. Upper limit is infinity. Mean of 0, standard deviation of 1. Right? Those are inherent features of the standard normal distribution z. So our p-value turns out to be 0.0188, which is in fact less than the alpha of 0.05 that we are using here. So we're going to reject the null hypothesis and support the alternative. So looking at our original hypotheses that we wrote down, we are rejecting the null, that the percentage is 15%, and we're supporting the alternative, that the percent is more than 15%. So I'm going to make a declarative statement. We have enough evidence to support. Of course, that we have enough evidence is kind of redundant, so we're just going to support the theory. So more than 15% of all Iditarod finishers are female. Just a straightforward statement. Example number 9. So this time we're going to look at how many calories the dogs are consuming per day in the race. And we want to know if the variance is less than 1 million calories squared. So the variance is what we're interested in, and we want to know if it's less than 1 million calories squared. This is going to be the alternative hypothesis. This is what we're going to attempt to prove. And you always try and prove what you're asked if it's something you can prove. And more, less, or not equal to is something that you can prove, potentially, depending on what your data turns out to be. All right, so we want to know if the variance, sigma squared, notice the squared on the sigma, is less than 1 million. So we will assume the null hypothesis, the variance is 1 million, no lower until we see some proof. We were given sample data that says the average number of calories was 10,072 and the standard deviation was 841 calories, but that was for 386 days. So we have a sample of 386 days worth of calorie consumptions. And so the average and standard deviation being given here are X bar and S. Okay, they're from the sample of 386 observations, not for the entire population, all calories consumed by all dogs all time. Now, important to note here, we were told to assume that calories per day are normally distributed. Okay, without that, we would be in trouble in this problem. Again, when we go to look at our equation, we want to test the variance. And the only condition that's required to test that variance is that our population that we're sampling from must be normal. So if the number of calories they consume per day are not normally distributed, we would be in trouble here. No, but since we're allowed to assume this, we are able to use our chi-square distribution test. Okay, so again, degrees of freedom n minus 1. We're going to plug in our values to calculate our test statistic. S was 841, so I have 841 squared, where S squared goes. But we are assuming that sigma squared is 1 million, so I put 1 million down here, no squaring, because it already is the assumed value of sigma squared. Again, we get our chi-squared score. Looks like a giant number, but chi-squared scores are very reliant and dependent on the degrees of freedom to know how big they are. So when we go to look at our graph, we have to know which tail we're interested in. We're trying to be convinced that the variance is small. So we're going to look at the sample variance. Now, we have the sample standard deviation here, S, right? And the smaller S is, the smaller the sample variance S squared would be. So if we want to be convinced that sigma squared is small, then S needs to be small, S squared needs to be small. So the smaller S is, right, then the smaller S squared is, and the more convinced I am that sigma squared is small. So more convincing data in this situation is a small value for S and S squared. So what happens when we have a small value of S? Okay, again, using our equation, small values of S make small chi-squared scores. And you replace 841 there with something smaller, we'd get a number smaller than 272. And the small chi-squared scores are to the left of the graph. So we have a chi-squared graph, 385 degrees of freedom because it's a sample size of 386. Keep in mind that the chi-squared distribution, the mean is equal to the degrees of freedom, but the standard deviation is the square root of 2 times the degrees of freedom. So here we have a giant standard deviation, which is why this graph is so wide and so short. We need to find the area to the left of our test statistic. So 0 is our lower limit on the chi-square graph. Our test statistic, 272.303185 with 385 degrees of freedom. And on my calculator, this comes back 3.1160299. As soon as I see that 3.11, my eyes go immediately to the right to find the scientific notation. The function I just used finds a probability. Probability must be between 0 and 1. I know 3.1 is not a correct response, so I know there must be scientific notation out there to the right. So we move the decimal place 6 places to the left. The first move puts it in front of the 3. 5 more moves gives me 5 zeros to start the number. And so our p-value here is way less than 0.05 or any other alpha we've ever used. So we are rejecting the null hypothesis, and we're rejecting it conclusively. Okay. And we are supporting the alternative hypothesis. All that's left to do is write our conclusion. We have rejected the null hypothesis, rejected the assumed value of sigma squared being 1,000,000. We're supporting the alternative to that sigma squared is less than 1,000,000. So we're going to make a statement. And that statement is that H1 is true, so H1 said the variance is less than 1,000,000 calories squared. So very conclusive. It's been proven beyond a reasonable doubt that p-value was so small. I would bet a lot of money on this. I'm very confident, because if the variance was 1,000,000 and no smaller, there'd be almost no chance to see the sample data we did randomly. And for our 10th and final example, we want to know if the average number of calories is 10,000 calories per day. Okay, so we go to write our hypotheses. Again, we're asked if this is the correct number. Remember, it is impossible to prove equality. So we're going to have to try and prove that the mean is not 10,000 calories per day. So we will assume that 10,000 is the correct number until we see some proof otherwise. We have the same information that we had a minute ago in the previous example. We have 386 observations, which had a sample average of 10,072 and a standard deviation of 841. So n, x bar, and s are known. We have to figure out our equation. To do that, we have to know that they're normally distributed. That comes into play, or at least it can come into play depending on the situation we're in. As we look at our formula sheet, we're interested in the mean. We don't know the standard deviation for all calorie consumptions. We just know for a sample of 386. And we were told to assume that the calorie consumption per day was normally distributed. This was critical when we did example 9, when we were testing the variance in the calories. Okay. Here, the assumption is not really needed because we have a sample size larger than 30, 386. So the behavior of x bar will resemble a normal curve. Okay, so x bar is going to be approximately normal. When we try and standardize it, however, we fail because we don't know sigma. So because we had to estimate sigma with S, the result is a t-score instead of a z-score. Remember, the t-distribution looks just like z, symmetric, centered with the mean of 0, but has a standard deviation slightly bigger than 1, allowing for a slightly higher probability of the extremely low and high values. So we have our equation, we plug in our numbers, assuming the null is true. Every single time I assume the null is true. And so once we have our equation, we have to know what side of the graph we want. So what are we trying to be convinced of? That the mean or average is not 10,000 calories. So I look at the sample mean. If I want to be convinced of something population-wide, I need to see that trait in the sample. Okay, so here my sample mean is 72 away from 10,000. So we have some evidence that the average might not be 10,000. How strong is that evidence? That's why we have to go through the test statistic and the p-value formalities. So if I want to be convinced that mu is not 10,000, that the average overall is not 10,000, when I take a sample, I need a sample mean, x bar, that is far away from 10,000. Right? The farther away from 10,000 that the sample mean is, the more convinced I am that the population mean is not 10,000. Now, this gives us two options. Right? When it comes to more convincing data, x bar could be very small, meaning much less than 10,000, or very big, which in this case means much more than 10,000. Looking at our test statistic, the value of x bar directly influences the t-score. The bigger x bar is, the bigger the t-score. The smaller x bar, the smaller the t-score. So we want small x bars, which means small t-scores would be acceptable. So left tail values for the t-score would be convincing, but also big x bars, which means big t-scores, and the right tail of the graph would also be convincing. So our t-score could be at the far left or far right of our t-graph. So either tail is going to be convincing. So this is a two-tailed test. The further our test statistic goes into either of the two tails, the more convinced we are that the mean is not 10,000. Now, we had 386 for our sample size, so I have 385 for my degrees of freedom. Okay. This is a two-tailed test. My test statistic happens to be in the right tail. So the area to the right of that test statistic is half my p-value. We're going to use the TCDF from our test statistic to infinity with 385 degrees of freedom, but that's only half of my p-value, so I need to multiply that by 2, giving me eventually a grand total of 0.0934 for my p-value. As always, we compare that p-value to alpha. That p-value is not less than alpha, so we failed to reject the null hypothesis, and because we failed to reject the null hypothesis, we cannot support the alternative. So writing our conclusion, we failed to reject the assumption that mu equals 10,000, which means we cannot support the alternative theory to that mu does not equal 10,000. So again, I cannot support, that's the whole, there's not enough evidence to conclude. And what can I not support? H1. And H1 said that the average number of calories consumed per day by the dogs competing in the Iditarod is not, that not is a critical word here, not 10,000 calories. There you have it, 10 complete hypothesis tests worked from start to finish. I know it took a long time, but there are a lot of details in there. So I hope this helps. Good luck and go Vols.